In this video, I'm going to talk about another type of regression pitfall, and that is multicollinearity. So multicollinearity occurs when we've got excessive correlation between quantitative predictors in the model that leads to unstable models and inflated standard errors. So we can identify this a few different ways. One is by looking at a scatterplot matrix. And so if we see in the scatterplot matrix that we've got very high correlations between some of the predictors, and in particular the correlations between the predictors look higher than correlations between the response variable and the predictors, then we may have a multicollinearity issue. We can also look at numerical summaries of those correlations in the individual scatterplots. So if we look at those bivariate correlations, and again note that those correlations between individual predictors tend to be higher than correlations between the response variable and predictors, then we may have a multicollinearity problem. And then another way of detecting multicollinearity, and this is perhaps the easiest way to do it, is if when we fit the model we select an option to have the variance inflation factors calculated, or we calculate those with a function after we've fit the model. We can look at those variance inflation factors, and so there's a variance inflation factor for each predictor in the model. And then the rule of thumb that we can use is there's potential problems, potential multicollinearity problems, if any of those variance inflation factors are greater than 4, and if any of those variance inflation factors are greater than 10, we've almost certainly got problems. So that's perhaps the easiest way to identify potential multicollinearity problems. So if we have got a potential multicollinearity problem, then what can we do? So it may be possible that we could go back and collect more data and try and collect data such that we don't have these multicollinearity problems. So if, say, we've identified a multicollinearity problem between x1 and x2, we could try and go out and collect more data such that there's not such a high correlation between x1 and x2 in our sample. That's a bit of a big ask in many cases, and it's probably not going to be possible in most cases to do this, but if it is possible, it's an ideal solution. Another possibility that's perhaps a little more realistic, if we can't go out and collect more data, is to look at where the problems are. So let's say it is x1 and x2 where the issue is. We can create a new combined predictor variable from x1 and x2 if we can combine those predictors in a meaningful way. And I'll actually show an example of this in the data that we'll look at in a second. Again, it's not always possible to do this. It very much depends on the particular application that we're looking at, whether combining predictors together is meaningful. The more common way of dealing with multicollinearity is, let's say we've got two multicollinear predictors in the model. Let's say, again, for sake of argument, it's x1 and x2. A common remedy, if neither of these first two ideas are possible, is to simply remove one of the highly correlated predictors from the model. And typically you might look at removing the one that's got the highest p-value in the model. Okay, so let's look at some data. So we've actually looked at this data before. This is some data where we're looking at sales and That's our response variable, and then our predictor variables, we've got two potential predictor variables. X1 is a measure of the amount of money that's been spent on traditional forms of advertising on television or in the newspaper, and then X2 is measuring the amount of money that's been spent on internet advertising. So I've got that data queued up here in R. We could take a quick look at it. So here's the data. It's not a huge data set. We could fit our model and summarize it, and oh, rats. That's not good. It looks like if I look at that p-value for this predictor, it's bigger than 0.05. It's not significant. So it looks like there's little evidence of a linear association between sales and traditional advertising for a fixed level of internet advertising. Similarly, if I look at this predictor, this tells me, again, it's not significant. It's above our usual significance level of 0.05, so that tells me that there's little evidence of a linear association between sales and internet advertising for a fixed level of traditional advertising. So that's a little bit disappointing, and it's a little bit strange too, because if we look at the value of R squared, it's 0.974. So this model can explain 97.4% of the variation in sales, yet neither predictor is significant. So this is a little bit strange. So what's going on? Well, if I look at, I want to look at a graph here. Okay, I'm just gonna do that right here. So I'm gonna see if I can do it on the fly here. Okay, there we go. So here's a scatterplot matrix of the three variables. So sales, traditional advertising, internet advertising. You can see there's a very strong correlation between all pairs of variables. In particular, this scatterplot here is traditional advertising on the vertical axis, internet advertising on the horizontal axis. There's a very strong correlation between those two predictors. And so this is a very clear sign of a potential multicollinearity problem. Another way to identify it is to calculate the variance inflation factors. So the variance inflation factors, 49.5 for each of those predictors, which is way above our threshold, our rule of thumb threshold. Anything above 4 is potentially going to be a problem. Anything above 10 is almost certainly going to be a problem. So here, these two variance inflation factors have almost certainly got a bit of an issue with multicollinearity. So what to do? Well, in this case, if I think about my two predictors, they're both measuring different forms of advertising. So what if I just add the two together and come up with a new predictor that's going to measure the total advertising spending? So I'm gonna lose a little bit of information doing that, because I'm not going to be able to break this down into different forms of advertising, but hopefully I'll still get an effective model that will tell me the relationship between overall advertising and sales. So let's do that, and then fit my new model and summarize it. And if we look at the value of R squared, it's pretty much the same. It was 0.974 before, now it's 0.9737, and look at the significance of my combined predictor. Highly significant. This number is 3.13 times 10 to the minus 9. It's essentially 0. T-statistic is huge. So in this case, we were able to solve the multicollinearity problem because it made sense to combine the two predictors in this way. And once we did that, we get a model that's quite effective. As I said before, though, it's actually much more common to have to drop one of those correlated predictors from the model. So that would be another way of handling this. So for example, we might decide that we're going to drop this predictor from the model, x1, because it's got the higher p-value. In this case, though, I think this approach that we used to add the two predictors together is more effective in this example. So that's another pitfall to look out for, is multicollinearity. In the next video, I'm going to consider another pitfall that we need to look for, and that is if we've got potential predictors that we've not included, and by not including those predictors, we've ended up with a model that's actually incorrect and potentially highly misleading. So that's what I'll look at in the next video.